London, March 1727. An old man lies dying in a room in Kensington, refusing treatment for the kidney stones that will kill him within hours. He is 84 years old. Outside this room, England waits. The nation understands that something unprecedented is ending. Never before has a scientist received a state funeral. Never before have dukes and earls carried a mathematician's coffin. This man unified heaven and earth with equations. He proved that the same force pulling an apple downward holds the moon in its orbit. He wrote laws that governed every falling object, every orbiting planet, every collision between bodies, from atoms to stars. For 2 centuries, his physics will remain unshaken. Even when Einstein supersedes him, Newton's laws will still launch rockets and build bridges, but the man himself remains a mystery. In this room full of papers, there are manuscripts on alchemy that dwarf his scientific writings. There are theological treatises denying the Trinity, kept hidden for fear of execution. There are letters revealing feuds so vicious they lasted decades, grudges nursed until enemies died. The Royal Society president who could destroy careers with a word. The natural philosopher who spent more hours trying to transmute lead into gold than calculating planetary orbits. The genius who may have discovered calculus but hid it for 20 years. The knight who was born in a farmhouse to an illiterate father who died before his birth. What made this mind? What wound drove him to decode the universe? And what does it cost to see further than anyone before you? Before we journey into the strangest genius the world has known, I want to ask something of you. If you find yourself pulled into this story, if you want to see more documentaries that reveal the human complexity behind historical greatness, take a moment now to like this video and subscribe to the channel. Your support makes this work possible. And I'm genuinely curious, where in the world are you watching from? Drop a comment and let me know. Now let's go back to the beginning, to a winter day in 1642, to a stone manor house in rural Lincolnshire, to a child born so small they said he could fit inside a quart pot. Christmas Day, 1642, Woolsthorpe Manor stands isolated in the Lincolnshire countryside, surrounded by fields and sheep. Inside, Hannah Newton gives birth prematurely. The baby is so tiny the midwives expect him to die within hours. They send someone to the village to fetch baptismal supplies, certain the child will not survive until morning. The father is already dead, buried 3 months earlier. Isaac Newton Sr., illiterate but prosperous, a yeoman farmer who owned this manor and the land around it, never saw his son. The baby, also named Isaac, does not die. Against expectation, he survives, but he enters the world marked by absence. No father, a mother exhausted from childbirth and widowhood, a country tearing itself apart in civil war. The midwives whisper among themselves about the fragile infant who clings to life with inexplicable tenacity. They have seen premature babies before, have watched them fade within days, sometimes hours. This one is different. Week follows week, and the tiny child persists. Hannah, grieving her husband and fearing for her son, spends sleepless nights listening to his breathing, waiting for it to stop. It does not stop. The infant who should not survive becomes a baby who will not die, as if sheer will compensates for physical weakness. This is England during the collapse. Parliament and King Charles battle for supremacy. Armies march through counties requisitioning food and horses. The social order that has held for centuries fractures. Within 7 years, the king will be beheaded. The boy growing up at Woolsthorpe inhabits a world where certainty has dissolved, where the unthinkable becomes real. Yet even as England tears itself apart, the rhythms of rural life continue. Sheep need tending, crops need planting, the manor requires maintenance. Woolsthorpe exists in a strange bubble, aware of distant conflict but not directly touched by it. News filters through slowly, carried by travellers and merchants. Parliamentary forces win a battle here, royalist forces there. The war is real but also abstract, something happening elsewhere to other people. But Woolsthorpe itself remains stable. Hannah manages the estate. The farm prospers. Isaac grows from fragile infant to small, quiet boy. He plays in the manor's rooms, in the surrounding fields. He is bright but unremarkable. No one sees genius. What they see is a fatherless child in a house full of absence. The boy develops slowly, cautiously, as if the weakness of his birth remains with him. He is smaller than other children, quieter, more inward. He watches more than he participates. When other children play rough games, Isaac stands at the edges observing. He notices things others miss. The way shadows move across the courtyard as the sun travels. The patterns birds make when they fly. The texture of stone and wood under his small fingers. He creates games for himself, solitary entertainments that require no other children. He arranges stones in patterns. He builds tiny structures from twigs. He discovers that water poured from different heights creates different sounds. These observations are not scientific yet, just the natural curiosity of childhood, but they reveal a mind that finds the physical world endlessly fascinating. Hannah watches her son with a mixture of love and bewilderment. He is not like other children. He does not run and shout. He does not demand attention. Instead, he seems content in his own company, absorbed in activities she does not understand. She wonders if the premature birth damaged something in him, if his strangeness is the price of his survival. She does not know that she is watching the early manifestation of a mind that will change how humans understand the universe. Then when Isaac is 3 years old, Hannah remarries. The groom is Barnabas Smith, an elderly rector from the nearby village of North Witham. Smith is 63, wealthy from his position and from previous good fortune. The age gap between him and Hannah is considerable. She is in her 30s, still relatively young, but Smith is established, respectable, a member of the clergy. The marriage offers financial security beyond what the farm provides. It offers status, it offers a future. There is only one condition. Smith will not take Hannah's son. The boy stays at Woolsthorpe. Hannah moves to her new husband's rectory a mile away. She leaves Isaac with his maternal grandmother, Marjorie Ayscough. The negotiations that lead to this arrangement are lost to history. Did Hannah protest? Did she try to insist that her son come with her? Or did she accept Smith's terms without argument, choosing security over motherhood? We do not know. What we know is the outcome. The 3-year-old is left behind. Imagine the 3-year-old mind trying to comprehend this. His mother leaves. She does not take him. She lives close enough that he might sometimes see her in the distance, but she has chosen a new life that does not include him. His grandmother, already elderly, becomes his guardian. The manor that should be full of family contains only the old woman and the abandoned child. What does a 3-year-old understand about such a situation? Does he think he has done something wrong, that he is being punished? Does he wait for his mother to return, believing her absence is temporary? Or does he, with the brutal clarity children sometimes possess, understand immediately that he has been chosen against, that his mother has selected a new husband over her son? The days must blur together in those early weeks after Hannah's departure. The house is quieter. Marjorie Ayscough is not unkind, but she is not a mother. She is a grandmother suddenly burdened with full-time care of a young child. She feeds him, clothes him, ensures he is safe. Emotional warmth, demonstrative affection, the physical closeness a child needs. These are not her strengths. Isaac learns to expect nothing. He learns not to reach for comfort because comfort is not offered. He learns to contain his emotions because expressing them brings no response. He learns, at an age when most children are learning to trust the world, that the world is fundamentally unreliable, that the people who should be constant can vanish without warning. And 1 mile away, in the rectory at North Witham, his mother lives with her new husband, close enough that Isaac might occasionally see the house when he is taken to the village. Close enough that he knows exactly where she is, not dead, not lost, simply choosing to be elsewhere. Years later, when Newton is 19, he will compile a list of sins in his notebook, among them, written in his own hand, threatening my father and mother Smith to burn them and the house over them. The rage is specific. Not just his stepfather, his mother too. The fantasy is complete. The house burning, the 2 people inside it consumed. The child who was left behind imagines destroying the place where his mother chose to be instead of with him. This entry appears in a document titled Peccata, Sins, compiled as part of Newton's religious self-examination. The list contains 58 sins, most relatively minor: lying, idle thoughts on Sundays, neglecting to pray. But this one stands out. This one reveals murderous fantasy directed at specific targets. The child who learned not to express emotion still felt emotion, and the emotion was volcanic rage contained beneath a surface of rigid control. This is the wound. This is the original trauma that will shape everything. The brilliant, paranoid, vengeful man who emerges will be comprehensible only through this lens. He was abandoned. He was chosen against. And some part of him will spend the rest of his life trying to achieve something so absolute that abandonment becomes impossible. But first, he must grow up in the grandmother's house. Marjorie Ayscough is not unkind, but she is old and practical. She manages the estate. She ensures the boy is fed and clothed. Emotional warmth is not her specialty. Isaac learns to be alone. He plays by himself. He builds things, small wooden objects, toys, models. He shows mechanical aptitude unusual for a child. He is quiet, inward, self-contained. The boy discovers that objects are more reliable than people. A wooden toy behaves predictably. If you push it, it moves. If you drop it, it falls. There are no surprises, no sudden abandonments. This realization, never articulated but deeply felt, shapes how Isaac relates to the world. People are dangerous. Objects are safe. Understanding how objects work is safer than trying to understand how people work. In the long afternoons at Woolsthorpe, Isaac develops an almost mystical relationship with physical objects. He spends hours examining how doors swing on hinges, how latches catch and release, how weight and leverage work together to move things. When the servants perform their work, he watches intently, not them, but the tools they use, the mechanics of their tasks. How does a broom sweep? How does water flow from a bucket? How does a candle burn? These are not idle wonderings. Isaac tests his theories. He tries different ways of pouring water to see how the flow changes. He examines burned candles to understand how wax melts and hardens. He takes broken tools apart to see their internal workings, earning the servant's exasperation when he cannot reassemble them. But failure does not discourage him. Each failure teaches something. Each broken mechanism reveals something about how it was supposed to work. Marjorie Ayscough watches her grandson with growing bewilderment. She loves him in her reserved way, but she does not understand him. Other grandchildren might want stories or games. Isaac wants string and sticks and scraps of metal. When she asks what he is making, he cannot always explain. Sometimes he does not know himself until the thing is finished. The creative process is mysterious even to him. He has an image in his mind of how something should work, and his hands try to make it real. The isolation of Woolsthorpe amplifies his inwardness. There are no neighbour children to play with. The estate workers have families, but their children are wary of the young master, the strange boy who talks to himself and builds incomprehensible contraptions. Isaac does not miss playmates. He does not seem to register their absence. His inner world is so rich, so populated with mechanical puzzles and physical questions, that external companionship feels unnecessary. He begins building more complex things. A cart with moving wheels. A windmill model that catches the breeze. These are not mere toys, but functioning mechanisms. Isaac observes real carts and real windmills, then recreates them in miniature. The process requires close attention, patient work, repeated failures followed by adjustments. For a child of 6 or 7, this level of focused effort is unusual. For Isaac, it is natural. He has learned to entertain himself, to find satisfaction in solitary achievement. But there is something else in these creations beyond mechanical interest. There is control. When Isaac builds a cart, he controls every aspect of its construction and operation. When he builds a windmill, he masters the principles that make it turn. The world of people is chaotic, unpredictable, dangerous. The world of mechanisms is ordered, comprehensible, safe. In the workshop of his mind, Isaac is not abandoned or unwanted. He is the master, the creator, the one who makes things work according to his will. In 1653, when Isaac is 10, Barnabas Smith dies. Hannah returns to Woolsthorpe, but she does not return alone. She brings 3 children from her second marriage, Mary, Benjamin, and Hannah Smith. The manor that was quiet now fills with half-siblings. Isaac must share his mother with children she chose to keep, children who had her presence during the years he did not. The hierarchy is clear. He is the eldest, the heir to the estate, but he is also the one who was left. The return transforms Woolsthorpe from a house of silence into a house of noise. 3 young children, Mary is 8, Benjamin 6, Hannah 4, fill rooms with their voices, their games, their demands. Hannah Smith, the mother who left, is now constantly occupied with these children. They need her attention, her care, her love. And Isaac watches from the margins, the strange eldest son who spent 7 years learning to live without her. Does Hannah try to re-establish connection with Isaac? Does she recognize the damage those 7 years have caused? We have no record of her attempts, if any existed. What we know is that Isaac remains peripheral. The half-siblings are young and needy. Hannah is busy. The farm requires management. Smith's estate has come to her, increasing her responsibilities. Isaac is 10 years old enough not to need constant supervision, young enough to still need a mother's affection. He receives supervision. Affection is less clear. Hannah's return changes the household, but not necessarily Isaac's position in it. She is busy with 3 young children. The farm requires management. Isaac remains somewhat peripheral, the strange eldest son who builds intricate mechanical devices and shows little interest in normal boyhood pursuits. The half-siblings are wary of their strange older brother. He does not play their games. He does not laugh at their jokes. He disappears for hours into his own pursuits. They learn to avoid him and he learns to avoid them. The manor contains 6 people living in different emotional worlds, connected by blood and proximity, but not by affection. At age 12, he is sent to King's School in Grantham, a market town 7 miles from Woolsthorpe. This is standard for a boy of his class. The school teaches Latin, Greek, mathematics, scripture. Isaac boards with William Clark, the local apothecary. The Clark household introduces him to something he has never experienced: intellectual materials. Clark has books. The apothecary's work involves substances, measurements, preparations. For the first time, Isaac encounters systematic knowledge. He excels at school, particularly in mathematics, but he is not merely studious. He is obsessive. He fills notebooks with notes, diagrams, lists. He builds a windmill model so accurate it could grind wheat. He constructs water clocks and sundials. The other boys notice he is different. He does not fit their world of rough play and social maneuvering. He fits the world of objects, mechanisms, principles. The Clark household is unlike Woolsthorpe in every way. William Clark is educated, curious, engaged with ideas. His apothecary shop contains jars of substances, scales for measuring, books describing properties and uses. This is Isaac's first exposure to systematic investigation of the natural world. Clark does not conduct experiments in the modern sense, but he does observe, record, and apply knowledge. Medicine in the 17th century is part empirical practice, part inherited wisdom, part superstition, but it requires more rigorous thinking than farming. Clark allows Isaac access to his books and materials. The boy who built wooden toys now encounters written knowledge. He reads about medicine, about substances, about properties of matter. He copies passages into notebooks, adding his own observations and questions. The notebooks reveal a mind that does not passively receive information, but actively interrogates it. "Why is this so?" appears frequently in the margins. "Test this" appears next, to claims that seem dubious. At King's School, Isaac's mathematical ability becomes apparent. The curriculum includes basic arithmetic and geometry. For most students, this is difficult material requiring patient memorization. For Isaac, it is obvious. He grasps mathematical relationships instantly. When the master demonstrates geometric proofs, Isaac sees 3 steps ahead. His classmates struggle. He is bored, but he is not popular. The other boys sense his difference and respond with the cruelty children often show toward those who do not fit. They mock his small size, his serious demeanor, his lack of interest in their pursuits. There are fights, though Isaac is not naturally combative. One incident becomes school legend. A bully challenges Isaac physically, and Isaac, smaller but furious, beats him decisively. Then, determined to defeat him in every way, Isaac surpasses him academically as well, rising to the top of the class. The story reveals something about Newton's character. Defeat is intolerable. Competition, once engaged, must be won completely. The windmill he builds during these years is extraordinary. A working windmill has been constructed near Grantham, and Isaac observes it carefully. He spends entire afternoons watching it, noting how the sails catch wind, how the grinding mechanism works, how the whole structure balances massive forces. Then he returns to his lodgings and begins building a scale model so accurate that it can grind wheat into flour. The construction takes weeks. Isaac carves wooden gears by hand, testing each one to ensure smooth meshing. He constructs the frame from scavenged wood, using techniques he has observed from carpenters. The sails are fabric stretched over wooden frames, angled precisely to catch maximum wind. When it is finally complete, the model works perfectly. Flour actually comes out, though in tiny quantities. The Clarks are amazed. The other boys at school are impressed despite themselves. But Isaac adds something the original lacks: a treadmill inside, where a mouse, he calls the miller, can power the mechanism when there is no wind. This is pure innovation. The real windmill depends entirely on wind. Isaac's model has a backup system. He trains the mouse, actually just allows it to run in the treadmill while searching for food, and demonstrates how mechanical motion can be generated by living muscle as well as natural force. The principle is the same: energy converted to rotation, rotation converted to grinding. The source of energy can vary. This combination of observation, recreation, and innovation is unusual for a teenager. It suggests a mind that sees how things work and immediately imagines how they could work differently. Most people observe and copy. Isaac observes, understands the underlying principle, then applies the principle in new ways. This is the beginning of the scientific method that will later characterize his mature work. Observe phenomena, extract principles, apply principles to new situations. The windmill becomes famous locally. People come to see it. Some offer to buy it, but Isaac refuses. It is not for sale. It is proof. Proof that he understands, proof that he can create, proof that his mind works differently than other minds. For a boy defined by what he lacks, father, mother's presence, social grace, this tangible achievement demonstrates what he possesses, an intellect that can decode and reconstruct the physical world. Then, in 1659, Hannah makes a decision that nearly ends everything. Isaac is 16. As the eldest son, he should manage the family estate. His education has been adequate for a farmer. She removes him from King's School and brings him home to learn agriculture. This is practical, conventional, exactly what should happen to a yeoman farmer's heir. The decision is economically rational. The estate requires management. Isaac is the heir. Training him to run the property makes sense. Hannah likely consults with advisors, with family members. Everyone agrees this is the proper course. No one considers that Isaac might be suited for something other than farming. Brilliance in mathematics does not seem relevant to managing sheep and crops. It is a disaster. Isaac has no interest in farming and no aptitude for it. He is supposed to supervise workers, manage livestock, travel to markets. Instead, he reads. He builds devices. He conducts what he later calls experiments. Servants report finding him under hedges with a book, while sheep wander into neighbors' fields. He forgets to attend markets, or arrives and spends the entire day reading instead of negotiating prices. He is completely unsuited to the life Hannah envisions. The specific failures become family stories, retold with exasperation, and, later, amusement. Isaac is sent to market with a servant. They arrive, and Isaac immediately finds a spot to sit and read while the servant conducts business. When the servant finishes and searches for Isaac, he finds him in exactly the same position, completely absorbed in his book, unaware that hours have passed. On another occasion, Isaac is supposed to supervise workers repairing a fence. He becomes fascinated by the mechanics of the gate latch and spends the afternoon redesigning it while the workers stand idle, wondering what they should do. Sheep escape into neighbors' fields because Isaac has forgotten to check the fences. Crops are planted late because Isaac does not notice the season changing. Account books go unupdated because Isaac finds arithmetic tedious when applied to mundane matters like grain prices. He can solve complex geometrical problems for the pleasure of solving them, but tracking farm expenses bores him into neglect. Hannah is frustrated. She has brought her son home to learn a necessary skill, and he is failing spectacularly. The farm does not need a mathematician. It needs a manager. Isaac cannot or will not become what she needs him to be. Two men intervene. Henry Stokes, the headmaster at King's School, recognizes that removing Newton from education is waste bordering on crime. William Ayscough, Isaac's uncle and a Cambridge graduate, agrees. Together they convince Hannah to reverse her decision. Isaac returns to King's School to prepare for university. It is an unlikely reversal. Most mothers would not be persuaded. Most boys removed from school would never return. But Stokes is persistent, and perhaps Hannah recognizes that her strange eldest son will never become a normal farmer. The arguments Stokes and Ayscough make are both practical and idealistic. Practically, Isaac is useless as a farmer. Continuing to train him for that role wastes time and risks the estate through mismanagement. Better to find a different path for him and hire competent managers for the farm. Idealistically, Isaac's mathematical talent is extraordinary. Wasting such talent is a sin against God, who distributed abilities for a reason. Isaac should go to university, should pursue scholarship, should become the kind of man his intellectual abilities suit him to be. Hannah's agreement is reluctant. She is a practical woman, and this plan sounds impractical. Scholars do not earn much. University costs money. But Stokes offers to waive tuition for Isaac's final year of preparation. Ayscough agrees to contribute to Cambridge expenses. Perhaps Hannah, observing her son's profound unsuitability for farming, recognizes that she must accept reality rather than continue forcing him toward work he will never master. In 1661, at age 18, Isaac Newton enters Trinity College, Cambridge. He arrives as a subsizar, the lowest student rank. Subsizars work to pay for their education, serving wealthier students, performing menial tasks. It is not degrading in the modern sense. Many students of modest means enter this way, but it is a reminder of his position. He is here on tolerance, on the efforts of men who argued for his potential. He carries the burden of proving them right. The journey from Woolsthorpe to Cambridge is 60 miles, several days by horse. Isaac travels with his few possessions, clothes, books, notebooks. He has no idea what to expect. He has never been this far from home. He has never lived among so many people. Cambridge is a city, small by modern standards, but enormous compared to Grantham or the isolated manor at Woolsthorpe. Trinity College is imposing, stone buildings arranged around courtyards, chapel, library, dining hall. Hundreds of students and fellows. The noise and activity overwhelm. Isaac is assigned a small room shared with another student. The space is cramped, cold, lit by candles that must be purchased. This will be home for the next several years. Cambridge in 1661 is intellectually conservative. The official curriculum still centers on Aristotelian philosophy taught in Latin. Natural philosophy means reading ancient texts and disputing their meaning. The mechanical philosophy emerging elsewhere in Europe, Descartes, Galileo, the experimental method, exists on the margins. Newton dutifully attends lectures and disputations, but his real education happens elsewhere. The official education is formal, ritualized, largely medieval. Students attend lectures where professors read from established texts and comment on them. Students participate in disputations, formal debates following rigid structures. The point is not to discover new knowledge, but to master existing knowledge, to learn the received wisdom of centuries. Aristotle on physics, Ptolemy on astronomy, Galen on medicine. These are authorities, and authority is to be respected, not questioned. Newton finds this stultifying. He attends because he must, but his mind is elsewhere. The lectures present a universe he instinctively knows is wrong. Aristotle claims that heavy objects fall faster than light objects. Newton has observed falling objects and knows this is false. Ptolemy's geocentric astronomy requires increasingly complex adjustments to match observations. Newton has read about Copernican heliocentrism and finds it more elegant. The entire system of received knowledge feels like a structure built on faulty foundations, impressive but ultimately unstable. He discovers books, not the prescribed texts, but the new works circulating among a few progressive scholars. He encounters Descartes' geometry. He reads works on optics and astronomy. He begins filling notebooks with his own investigations. These are not lecture notes. They are original inquiries. He poses questions and works through them with relentless logic. The notebooks reveal a mind that does not accept authority. If Aristotle says something, Newton tests it. If Descartes proposes a theory, Newton examines its foundations. One notebook from this period survives, and its title is revealing: Questiones quaedam philosophicae. Certain philosophical questions. The questions range across natural philosophy. What is matter? What is light? What is motion? Newton does not merely summarize what authorities say. He evaluates, critiques, proposes alternatives. On the first page, he writes a motto: Amicus Plato, amicus Aristoteles, magis amica veritas. Plato is my friend. Aristotle is my friend, but my best friend is truth. This is declaration of independence. Authority matters less than correctness. Reputation matters less than evidence. In 1664, he encounters Isaac Barrow, the newly appointed Lucasian professor of mathematics. Barrow is only 12 years older than Newton, brilliant and generous. He recognizes something in the strange, quiet undergraduate. He lends Newton books. He allows him access to advanced materials. Under Barrow's indirect mentorship, Newton begins to develop the mathematical methods that will become calculus. He does not call it that. He calls it the method of fluxions. The concept is motion treated mathematically, change captured in equations. It is entirely original. No one has taught him this. He has invented it because he needed it to solve problems that interested him. The relationship between Barrow and Newton is not warm or personal. Barrow is a mentor in the intellectual sense, not the emotional sense. He sees Newton's ability and provides resources. He does not provide friendship. This suits Newton, who does not seek friendship. He seeks knowledge, and Barrow can help him access it. The method of fluxions emerges from Newton's attempt to solve a specific problem, finding the area under curves. Mathematicians have long struggled with this. The ancient Greeks developed methods for a few simple cases, but general solutions remained elusive. Newton approaches the problem by thinking about motion. If a point moves along a curve at varying speed, the area under the curve is related to the accumulation of that motion over time. By treating curves as generated by moving points, by thinking of quantities as flowing, Newton can calculate instantaneous rates of change and accumulated totals. This insight will revolutionize mathematics, but Newton does not immediately recognize its importance. For him, it is simply a useful tool for solving problems. In 1665, Newton receives his Bachelor of Arts degree. He has been at Cambridge 4 years. He is 22. His performance has been good enough to suggest he might pursue a fellowship, might remain in the academic world. Then the plague arrives. The Great Plague sweeps through England in 1665. London suffers catastrophically. Cambridge closes the university as precaution. Students and fellows scatter to family estates and villages. Newton returns to Woolsthorpe. It seems like an interruption, a temporary exile from the intellectual world. It becomes something else entirely. The plague is terrifying in its randomness. It kills rich and poor, young and old. Entire families die within days. Streets empty as survivors flee. London's death toll reaches 70,000. Cambridge, smaller and less densely populated, acts preemptively, sending students and fellows away before the plague can establish itself. No one knows when the university will reopen. It might be months, it might be longer. The Woolsthorpe years, 1665 to 1667, will later be called Newton's Annus Mirabilis, his year of miracles. Newton himself will cultivate this mythology, suggesting that in this brief period of isolation, he made virtually all his major discoveries. The truth is more complex and more interesting. He does not invent modern physics in 18 months. What he does is conduct a series of private investigations that establish foundations for everything that follows. And he does this in complete isolation, with no collaborators, no oversight, no audience except himself. At Woolsthorpe, he experiments with light. He obtains prisms and studies how they split white light into colours. The accepted theory, derived from Aristotle, holds that prisms somehow modify or corrupt light, adding colour to pure whiteness. Newton suspects this is wrong. He devises experiments. He allows sunlight through a small hole into a darkened room, passes it through a prism, observes the spectrum cast on the opposite wall. Then he takes a second prism and passes one colour of the spectrum through it. The colour does not change. It does not split further. This proves something extraordinary. White light is composite. The prism does not add colour. It separates the colours already present. White light contains the entire spectrum, and the prism merely reveals this. The experiments require patience and precision. Newton darkens a room by covering windows with shutters, then makes a small hole to admit a single beam of sunlight. The beam must be narrow, controlled. He positions the prism carefully, adjusting angles to produce clear spectra. He observes that different colours refract by different amounts. Red bends least, violet most. This suggests that colours are inherent properties of light, not modifications imposed by the prism. The crucial experiment is the experimentum crucis, the test that settles the question definitively. Newton takes the spectrum produced by one prism and selects a single colour using a screen with a narrow hole. He passes this isolated colour through a second prism. If the prism adds colour by modifying light, the second prism should produce new colours. It does not. The isolated colour refracts, but does not change hue. Blue light remains blue. Red light remains red. This proves that white light is composite and that colours are fundamental, not derivative. It is a simple experiment but revolutionary in implication. Light is not what anyone thought. And the method Newton uses, controlled experimentation, systematic variation of conditions, logical deduction from results, this method will become the template for experimental science. Newton does not stop with light. He conducts further experiments on colour, on how colours mix, on why objects appear the colours they do. He concludes that objects are coloured because they reflect certain colours and absorb others. A red apple appears red because it reflects red light and absorbs other colours. This is correct and, at the time, completely novel. Simultaneously, he works on mathematics. The method of fluxions continues to develop. He can now calculate rates of change, areas under curves, tangents to curves at any point. He is inventing integral and differential calculus, though he does not publish any of this. He keeps it in notebooks, private tools for his own investigations. He develops what he calls the binomial theorem, a method for expanding algebraic expressions of the form a plus b raised to any power. This might seem abstract and specialized, but it proves immensely powerful in solving equations and analyzing series. Newton discovers that the theorem works not just for whole number exponents, but for fractional and negative exponents as well, vastly expanding its utility. Again, this is original work, discovered independently because Newton needed it. And he thinks about gravity. The famous apple story originates here, though not in the form legend presents. Newton does not experience sudden revelation when an apple hits his head. That is later embellishment. What he recounts decades later is watching an apple fall and asking a question, Why does the apple fall straight down? Why not sideways or upward? The answer seems obvious. Gravity pulls it. But then Newton extends the thought. If gravity pulls the apple from the tree and gravity pulls objects from any height, how high does gravity extend? To the top of a mountain? To the clouds? To the moon? The insight is that gravity might be universal. The force pulling the apple might be the same force holding the moon in orbit. This is conceptually radical. Terrestrial and celestial physics have always been separate domains. Things on Earth fall because they seek their natural place. Things in the heavens move in perfect circles because they are made of quintessence, a fifth element beyond Earth: air, fire, and water. Newton's intuition violates this ancient division. What if there is one physics, one set of laws governing everything? He begins calculating. If the moon is held in orbit by Earth's gravity, then the force must decrease with distance. Otherwise, all objects, regardless of distance, would fall at the same rate, which is obviously false. But how does force decrease? Newton suspects an inverse square relationship. Double the distance, and the force becomes 1/4. This is geometrically elegant and matches what he knows about light intensity, which also follows an inverse square law. He performs a rough calculation using the known period of the moon's orbit and an estimate of the moon's distance. The numbers almost work, but not quite. The discrepancy bothers him, but not enough to resolve immediately. The fundamental insight is there. Gravity is universal, decreases with the square of distance, and governs both terrestrial and celestial motion. The precise proof will wait. He cannot yet prove this. He lacks the mathematics to handle orbital mechanics rigorously. He does not know the exact distance to the moon or the precise period of its orbit. But he has the conceptual framework. Gravity as a universal force. Mathematical laws applying equally to apples and moons. This will gestate for 20 years before he can fully develop it. These are the Woolsthorpe years, 22 months of isolation during which one of the greatest minds in history, freed from institutional obligations and social distractions, pursues knowledge for its own sake. No one directs him. No one evaluates him. He follows curiosity wherever it leads, and it leads to places no one has been before. The daily rhythm of these months follows a pattern that will characterize Newton's working life. He rises early, before dawn often, and begins work immediately. There is no formal structure to his day, no schedule imposed from outside. He works when inspiration strikes, which is almost always. He eats when hunger becomes impossible to ignore, which is often late. He sleeps when exhaustion overtakes him, which is usually in the small hours of morning. His room at Woolsthorpe fills with papers. Notebooks containing calculations pile on every surface. Diagrams cover loose sheets scattered across the floor. The prism experiments require darkness, so Newton covers windows during daylight hours, creating an artificial cave where colored light can be studied without interference from ambient illumination. Neighbors who glimpse the darkened room wonder what the young man is doing. Alchemical experiments, some speculate darkly. Witchcraft, others whisper. They are wrong, but not entirely wrong. What Newton is doing is equally mysterious, equally outside normal experience. He talks to himself during these experiments, a habit that will persist throughout his life. Colleagues at Cambridge will later report hearing Newton muttering as he works, conducting dialogues with invisible interlocutors, arguing with himself about problems and solutions. The self-talk is not madness, but method. By externalizing his thought process, he can examine it more clearly. By speaking objections aloud, he can refute them more rigorously. His mind operates at such intensity that keeping everything internal feels limiting. The notebooks from Woolsthorpe reveal the raw process of discovery. Unlike published works, which present conclusions cleanly, These private pages show false starts, corrections, sudden insights. On one page, Newton calculates the moon's orbit using one estimate of its distance. The numbers do not work. He tries again with different assumptions. Still not quite right. He makes a note to find better distance measurements. Years later, with more accurate data, he will return to these calculations and find that his method was correct. Only the input data was flawed. The prism work produces pages of observations written in his precise, controlled hand. Blue light bends more than red. White light contains all colors. The prism does not create color, but reveals color already present. Each statement is followed by pages of experimental details documenting how he reached that conclusion. Newton is not guessing. He is building knowledge systematically, one verified observation at a time. But the isolation is also literal. Newton is alone at Woolsthorpe. His mother and half-siblings are there, but he does not confide in them. They do not understand his work, and he does not expect them to. He works in private, in his room or outdoors, conducting experiments and filling notebooks with calculations. The great discoveries are made in solitude, witnessed by no one, validated by no one. Newton does not need validation. He trusts his own reasoning with absolute confidence. When he emerges from these working sessions, blinking in sunlight, he is disoriented. The world of family concerns and farm management feels distant, unreal. The real world is the world of forces and motion, of light and color, of mathematical patterns underlying physical phenomena. This is not affectation or pretension. Newton genuinely finds the abstract more concrete than the everyday. Equations feel more solid than matter. Principles feel more permanent than people. His family learns to leave him alone. When Isaac is working, he might as well be in another country. He does not hear questions. He does not notice meals. Time passes differently for him. What feels like an hour might be 6 hours. What feels like a brief calculation might take 2 days. The obsessive focus is both gift and curse. It allows unprecedented concentration on problems, but it also removes him from human connection. The abandoned child has grown into the self-exiled adult, choosing isolation because isolation enables the work that gives his life meaning. In 1667, the plague recedes, Cambridge reopens, Newton returns. He is 24 years old. He has conducted some of the most important scientific work in history, and no one knows about it. He has published nothing. He has told almost no one. The notebooks at Woolsthorpe contain insights that would revolutionize natural philosophy, and they remain his private property. At Cambridge, he is elected a Fellow of Trinity College. This provides housing, a stipend, and most importantly, freedom to continue his work. He is no longer a subsizar. He has achieved a position of modest security. But the fellowship comes with requirements. He must take holy orders within 7 years. He must profess belief in the 39 articles of the Church of England, including the doctrine of the Trinity. This will become a problem because Newton does not believe in the Trinity. He is developing, through private study of Scripture, an Arian theology that denies Christ's divinity. He keeps this completely hidden. Discovery would mean expulsion, possibly worse, so he lives with a secret that would destroy him if revealed. Newton's theological investigations are as intense as his scientific work. He reads the Bible in Greek and Latin, comparing translations, analyzing passages, constructing chronologies. He studies church history, tracing how doctrines developed over centuries. He concludes that the Trinity is a corruption, a doctrine imposed by 4th century councils for political reasons rather than scriptural truth. Christ was the Son of God, but not God himself. This is Arianism, a heresy condemned by the Church since the Council of Nicaea in 325. For Newton, this is not idle speculation. This is truth discovered through rigorous investigation. But it is truth that cannot be spoken. The Church of England is the official state religion. Denying the Trinity is heresy, punishable by loss of position at minimum, possibly by imprisonment. Newton writes his theological conclusions in manuscripts he hides carefully. He tells no one, or almost no one. The secret shapes his life, adding another layer of isolation. He cannot share his deepest convictions. In 1669, Isaac Barrow makes an extraordinary decision. He resigns the Lucasian professorship of mathematics and arranges for Newton to succeed him. Barrow is only 38 at the height of his intellectual powers, but he recognizes that Newton surpasses him. The professorship provides a salary and requires only annual lectures. For Newton, it means financial security and official sanction to pursue research. He is 26 years old, Lucasian professor of mathematics at Cambridge, holder of a chair that will later be occupied by Stephen Hawking. Barrow's resignation is unusual but not unprecedented. He has decided to focus on theology, and he recognizes that his mathematical abilities, considerable as they are, do not match Newton's. By stepping aside and ensuring Newton's appointment, Barrow performs an act of generosity rare in academic life. He prioritizes the advancement of knowledge over personal ambition. Newton accepts the position with little outward emotion. He does not express gratitude effusively. He does not celebrate. He simply assumes the responsibilities. The professorship requires him to deliver lectures, which he does with minimal enthusiasm. The position also provides the resources and legitimacy he needs to continue his work without interference. He lectures on optics, presenting his discoveries about light and color. The lectures are sparsely attended. Students find them difficult and abstract. Newton does not adjust his presentation to his audience. He presents what he has discovered and expects listeners to follow. If they cannot, that is not his concern. The lectures are later published as optical lectures, providing a record of Newton's thinking during this period. They are dense, mathematical, uncompromising. Newton does not write for a general audience. He writes for the few people capable of understanding him. This approach characterizes much of his work, rigorous, precise, inaccessible to all but the most dedicated readers. But lectures are private performances. What catapults Newton into public scientific controversy is publication. In 1672, he writes a paper titled New Theory about Light and Colours and submits it to the Philosophical Transactions of the Royal Society. The paper presents his prism experiments and his conclusion that white light is composite. It is Newton's first public scientific communication. He is 30 years old. The paper is clear, structured, persuasive. Newton describes his experiments in detail, explains his reasoning, presents his conclusions. He expects recognition. What he receives is criticism. The response shapes the rest of his life. Some fellows of the Royal Society are intrigued, but Robert Hooke, the Society's curator of experiments and a formidable natural philosopher in his own right, writes a response criticizing Newton's conclusions. Hooke does not dispute the experimental results, but he disagrees with Newton's interpretation. He proposes an alternative theory based on wave motion. The criticism is not dismissive. Hooke acknowledges the quality of Newton's work, but it is public disagreement. Newton reacts with fury. He writes lengthy rebuttals. He takes Hooke's criticism as personal attack. He complains to Henry Oldenburg, the Royal Society secretary, about the injustice of being questioned. The intensity of Newton's reaction reveals something about his psychology. He cannot tolerate criticism. He experiences disagreement as persecution. The wounds from childhood have created a person who must be right. must be unassailable, because to be wrong is to be worthless, to be abandonable. Newton's responses to Hooke are detailed and cutting. He dissects Hooke's objections point by point, demolishing them with logic and evidence. But the tone is not collegial. It is hostile, dismissive, contemptuous. Newton does not treat Hooke as a fellow investigator offering alternative hypotheses. He treats him as an enemy who must be defeated utterly. The Hooke controversy drags on for months. Other natural philosophers weigh in. Continental scientists like Christian Huygens offer their own objections. Newton responds to each criticism with increasing irritation. Finally, he threatens to withdraw from scientific communication entirely. He writes to Oldenburg that he regrets ever publishing anything, that the controversies are not worth the trouble. This is not empty threat. Newton means it. He will not publish his major works on mathematics and gravity for years, partly because he does not want to endure criticism. The feud with Hooke enters a cold phase. The two men avoid direct interaction, but the animosity remains. Hooke, based in London at the Royal Society, represents the experimental, collaborative approach to natural philosophy. Newton, isolated at Cambridge, represents the solitary, mathematical approach. They are rivals not just personally, but methodologically, and Newton, who holds grudges with archival precision, will remember every slight. In 1679, Hannah Newton dies. Isaac is 36. His relationship with his mother has been complicated by abandonment, by the years she chose someone else, by the half-siblings who shared her in ways he did not. We have no record of his reaction to her death. He does not write about it. He does not memorialize her. In the great sweep of his life, as biographers reconstruct it, her death is a date, a fact, nothing more. But for a man shaped by maternal abandonment, her death must register. She is gone, and with her any possibility of repair, of explanation, of reconciliation. The silence about Hannah's death is revealing. Newton, who keeps meticulous records of experiments and calculations, who writes thousands of pages on alchemy and theology, who preserves letters and documents, leaves nothing about his mother's passing. Was there grief, relief, indifference? We cannot know. The absence of evidence suggests feelings too complex or too painful to articulate, even in private writings. The same year, Robert Hooke, attempting reconciliation or perhaps genuine scientific collaboration, writes to Newton asking about his thoughts on planetary motion. Hooke has been developing a theory that planets move in ellipses due to a central attractive force that weakens with distance. He wonders if Newton has considered this problem. Newton responds curtly. He sketches a diagram showing what path a falling object would take if Earth did not obstruct it, a spiral into the center. Hooke writes back pointing out an error in Newton's diagram. If the attractive force follows an inverse square law, the path would not be a spiral, but an ellipse. Newton does not reply, but Hooke's letter has planted something, or perhaps reawakened something from the Woolsthorpe years. The question of orbital mechanics, of the mathematical relationship between force and motion, begins to occupy Newton again. Over the next several years, working in private, he develops the mathematical framework to prove what Hooke suggested. If gravity decreases with the square of distance, planetary orbits must be ellipses, but he does not publish this either. He does not tell Hooke. He solves the problem, the greatest problem in natural philosophy, the question that has occupied astronomers since Kepler described elliptical orbits without explaining their cause, and he writes the solution in a notebook and does nothing with it. Why the silence? Part of it is Newton's nature. He works for his own satisfaction, not for public recognition. Publication means exposure, criticism, controversy. better to solve problems privately and avoid the unpleasantness, but part of it is also vindictiveness. Hooke pointed out an error, however politely. Newton will not give him the satisfaction of being right, of seeing the solution. If Newton cannot be first and sole discoverer, he will withhold discovery entirely. In 1684, three men meet in a London coffee house: Robert Hooke, Edmund Halley, and Christopher Wren. They are discussing the inverse square law of gravity. All three suspect it explains planetary motion, but none can produce a mathematical proof. Wren offers a prize, a book worth 40 shillings, to whoever can demonstrate the connection between inverse square gravity and elliptical orbits. Halley decides to visit Cambridge and ask Newton, who has a reputation for mathematical prowess. In August 1684, Halley arrives at Newton's rooms in Trinity College. He poses the question: if gravity decreases with the square of distance, what path would a planet follow? Newton answers immediately: an ellipse. Halley is stunned. How does Newton know? Newton says he has calculated it. Halley asks to see the calculation. Newton searches through papers but cannot find it. He promises to send it to Halley. The casual way Newton answers reveals how differently he thinks. The problem that has stumped London's leading natural philosophers is, for Newton, already solved. He worked it out years ago and has moved on to other questions. The calculation is somewhere in his papers, but he has not bothered organizing or preserving it systematically. Halley's visit forces Newton to reconstruct the proof. Several months later, Halley receives not a brief calculation but a 9-page treatise titled De Motu Corporum in Gyrum, on the motion of bodies in an orbit. It contains complete proofs of planetary motion under inverse square gravity. Halley realizes he is holding something extraordinary. This is not just an answer to one question, this is a new foundation for all of physics. Halley returns to Cambridge and urges Newton to expand the work into a complete treatise. Newton, for reasons unclear, perhaps Halley's enthusiasm, perhaps the intellectual challenge, perhaps a sense that this work must finally be made public, agrees. He begins writing what will become Philosophiae Naturalis Principia Mathematica, the mathematical principles of natural philosophy. The composition of the Principia is one of the most intense intellectual efforts in history. For 18 months, Newton works obsessively. He stops attending meals. He forgets to sleep. Colleagues report finding him still working at dawn, unaware that night has passed. He is not writing a textbook. He is constructing a complete mathematical physics, proving every proposition from first principles. The work consumes him utterly. Newton's rooms at Trinity become a hermitage dedicated to a single purpose. Papers accumulate in drifts across every surface. Calculations cover the walls where he has run out of paper. Candles burn through the night, their wax dripping onto manuscripts, sealing observations under hardened puddles. The college servants who bring food find it untouched hours later. The bedclothes remain undisturbed for days at a time. Newton exists in a state of continuous intellectual arousal that transcends physical needs. His handwriting during this period deteriorates from his usual precise script into hurried scratches, as if his hand cannot keep pace with his mind. Corrections and insertions fill margins and spaces between lines. Some pages are crossed out entirely and rewritten. Others bear diagrams so dense with notation they become nearly incomprehensible. This is genius captured in real time, unfiltered and unpolished. The mathematical rigor Newton demands of himself is exhausting even to read. Every proposition builds on previous propositions. Every proof must be airtight, admitting no logical gaps. He writes in the style of Euclid, using geometric demonstrations rather than algebraic shortcuts. This makes the work more difficult to compose and more difficult to read, but also more irrefutable. Critics can dispute an algebraic result, but a geometric proof, properly constructed, is undeniable. Friends worry about his health. Edmund Halley visits periodically and finds Newton gaunt, hollow-eyed, existing on what seems to be nervous energy alone. Halley urges him to rest, to eat properly, to step away from the work. Newton agrees absently, then returns to his calculations the moment Halley leaves. The Principia has become an obsession bordering on possession. Newton must finish it. The work will not release him until it is complete. There are moments of breakthrough that colleagues later recall with awe. Newton would stare at a page for hours, motionless, completely absorbed. Then suddenly he would seize his pen and write furiously, pages filling with solutions to problems that had blocked him for days. The mental process was invisible, but its products were extraordinary. Problems that had defeated mathematicians for centuries yielded to Newton's sustained assault. There are also moments of despair. Some problems resist even Newton's abilities. He batters against them day after day, trying approach after approach, finding each one blocked. These failures drive him to fury. Papers are crumpled and thrown. Books are slammed shut. He paces his rooms like a caged animal, muttering angrily to himself. But he does not give up. He cannot give up. The problem exists, therefore a solution exists, and he will find it even if it takes weeks. The physical toll is severe. Newton loses weight he cannot afford to lose, his already thin frame becoming skeletal. His eyes develop a permanent redness from strain and lack of sleep. His hands shake slightly from exhaustion. But the mind remains sharp, perhaps sharpened by the physical deprivation. Some part of him has left behind the mortal body entirely and exists purely as intellect, as disembodied reasoning solving the puzzle of cosmic mechanics. The Principia's structure is rigorous to the point of severity. Book 1 develops the mathematics of motion and force. Book 2 analyzes motion in resisting mediums. Book 3 applies these principles to the system of the world, demonstrating that celestial mechanics and terrestrial mechanics are identical. The three laws of motion that open the work, objects remain at rest or in motion unless acted upon, force equals mass times acceleration. Every action has an equal and opposite reaction. These become the axioms of physics for 2 centuries. But the Principia's central achievement is the law of universal gravitation. Every particle attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. This single law explains why apples fall, why the moon orbits Earth, why planets orbit the sun, why tides rise and fall. It unifies phenomena that had always been considered separate. It reveals that the universe operates according to mathematical laws that human minds can comprehend. During the Principia's composition, Robert Hooke creates a final crisis. When he learns that Newton is writing a comprehensive work on celestial mechanics, he writes claiming priority for the inverse square law. Hooke argues that his 1679 letter to Newton suggested this relationship, and Newton should acknowledge him in the work. This is technically true but profoundly misleading. Hooke suggested the possibility. Newton proved it mathematically, derived its consequences, and constructed a complete theoretical framework. The difference between suggestion and proof is the difference between speculation and science. Newton's reaction is volcanic. He threatens to suppress Book 3 of the Principia entirely, the section applying his mechanics to astronomy. If Hooke wants credit, Newton will deny the world the fruits of his work. Halley, who is financing the Principia's publication from his own funds because the Royal Society lacks money, must mediate. He soothes Newton's rage, convinces him that Hooke's claim is trivial, persuades him to complete the work. Newton agrees but refuses to mention Hooke anywhere in the Principia. Where earlier drafts acknowledged Hooke's correspondence, the published version removes all references. It is scholarly vindictiveness on a grand scale. The Principia is published in 1687. Newton is 44 years old. The work's impact is immediate among those capable of understanding it, which is not many people. The mathematics is forbidding. Newton writes in the style of classical geometry rather than the algebraic methods becoming standard, partly to make the work more rigorous, partly to obscure his use of calculus, which he still has not published. Continental natural philosophers struggle with the Principia's methods and resist its conclusions. The idea of gravity as action at a distance, one body affecting another across empty space with no intervening mechanism, strikes many as a cult, a return to medieval thinking. But those who master the Principia recognize it as definitive. Edmund Halley writes a Latin ode printed in the front matter, praising Newton for revealing the design of the heavens. The work spreads through Britain, then Europe. It will take decades for Newtonian mechanics to fully displace Cartesian physics on the continent, but the process is inexorable. The Principia is too powerful, its predictions too accurate to be ignored. Newton's life changes. He is famous, at least among the small community of natural philosophers and mathematicians. Cambridge becomes constraining. In 1689, he is elected to Parliament representing the university. This brings him to London, into contact with political and social circles beyond academics. He meets John Locke, the philosopher, and they form a close friendship. He corresponds with other prominent thinkers. He is no longer the isolated professor conducting private research. He is a public figure. But something is breaking. In the early 1690s, Newton befriends Nicolas Fatio de Douillet, a young Swiss mathematician. The friendship is intense. Fatio visits Cambridge, stays with Newton, works with him on mathematics. Newton's letters to Fatio use language of unusual warmth for a man normally so guarded. Some biographers suggest romantic attachment. Others caution against reading too much into early modern epistolary conventions. What is clear is that the relationship matters deeply to Newton. In 1693, the friendship ends abruptly. We do not know why. Fatio stops visiting, the correspondence ceases, and Newton suffers a mental breakdown. He sends bizarre letters to Samuel Pepys and John Locke, accusing them of trying to embroil him with women and other strange offences. Locke, alarmed, writes to friends asking if Newton has lost his mind. Pepys is baffled. Newton later apologizes, claiming he has been unwell, but the episode reveals fragility beneath the genius. What caused the breakdown? Theories proliferate. Mercury poisoning from alchemical experiments. Newton has been conducting alchemy for decades, and mercury vapor accumulates in closed rooms. Exhaustion from overwork. The end of the Fatio friendship. A spiritual crisis. Analysis of hair samples in the 1970s shows elevated mercury levels, supporting the poisoning theory. But psychological explanations are equally plausible. Newton is 50 years old, famous but isolated, devoted to work that increasingly feels marginal. He has spent years writing theological treatises denying the Trinity, manuscripts that must be kept absolutely secret. He has pursued alchemy without achieving transmutation. The centre may not be holding. Newton recovers, but something has shifted. In 1696, he accepts appointment as Warden of the Royal Mint, a bureaucratic position overseeing coinage. This seems inexplicable. The Lucasian professor, author of the Principia, abandoning natural philosophy for administrative work. But the Mint provides substantial salary, a house in London, and escape from Cambridge. Newton moves to London and throws himself into mint operations with the same obsessive energy he once applied to physics. He pursues counterfeiters ruthlessly. He reorganizes the recoinage necessitated by degraded currency. He is effective and powerful. In 1699, he is promoted to Master of the Mint, a position he holds until death. The salary is substantial, far more than a professor earns. Newton becomes wealthy. He maintains a household in London.
His niece Catherine Barton, daughter of his half-sister Hannah, comes to live with him and manage his domestic affairs. Catherine is beautiful and charming, everything Newton is not. She becomes his hostess, his public face. In 1703, Robert Hooke dies. Newton, who has been a Fellow of the Royal Society since 1672 but has avoided active participation while Hooke lived, immediately becomes president of the Royal Society. He will hold this position for the rest of his life. As president, he wields enormous power. He controls what gets published in philosophical transactions. He influences who receives recognition and who faces obstruction. And he uses this power to settle scores. In 1704, Newton finally publishes Optics, a comprehensive work presenting his experiments and theories on light. He has delayed publication for 30 years, waiting for Hooke to die. The book appears in English rather than Latin, making it accessible to a broader audience. Unlike the geometrical severity of the Principia, Optics is experimental and observational. It describes prism experiments in detail, analyzes the colors of thin films, investigates refraction and reflection. The appendix includes mathematical methods Newton has developed but never published. Optics becomes hugely influential in establishing experimental methodology as central to natural philosophy. But the same year brings the beginning of another feud, one that will consume Newton's later years with even more bitterness than the Hooke conflict. Gottfried Wilhelm Leibniz, the German mathematician and philosopher, has independently invented calculus. Leibniz published his version in the 1680s using notation that will become standard. Newton's method of fluxions predates Leibniz's work, but Newton has not published it. Both men legitimately invented calculus independently, using different notation and approaching from different philosophical foundations. This should be celebrated as parallel achievement. Instead, it becomes a priority war. Newton's supporters, particularly British mathematicians, begin accusing Leibniz of plagiarism. They claim Leibniz saw Newton's unpublished manuscripts during a visit to London in 1676 and stole the ideas. Leibniz responds with his own priority claims. The dispute escalates. The Royal Society, now under Newton's presidency, forms a committee to investigate. The committee produces a report supporting Newton's priority. Later, historians discover that Newton himself wrote much of the report, anonymously. He orchestrated a supposedly impartial investigation to destroy his rival's reputation. The calculus priority dispute is uglier than the Hooke controversy because it is international and ideological. British mathematics versus continental mathematics. Newton's geometric methods versus Leibniz's algebraic approach. National pride entangles with personal vindictiveness. Newton pursues the campaign against Leibniz with relentless energy. He writes anonymous attacks, he mobilizes supporters. He uses his position as Royal Society president to control the narrative. Leibniz, isolated in Hanover, cannot effectively counter the assault. The dispute poisons European mathematics for decades. What drives this behavior? Why does the author of the Principia, secure in his achievements, need to destroy rivals? The psychological pattern is consistent. Newton cannot tolerate the possibility that someone else might receive credit for something he discovered. Priority is not merely professional recognition, it is existential validation. To be anticipated is to be rendered worthless. The abandoned child still operates in the elderly knight, needing absolute assurance that he is first, that he is indispensable, that he cannot be replaced or forgotten. Meanwhile, Newton continues his private studies. He spends enormous time on biblical chronology, attempting to date events in Scripture using astronomical calculations. He writes hundreds of pages on church history and theology, arguing the Trinitarian doctrine was a 4th century corruption of original Christianity. These manuscripts are never published. Newton guards them carefully. Discovery would mean scandal, possible charges of heresy, but he cannot stop writing them. Decoding Scripture feels as important as decoding nature. Both are divine texts that reveal hidden truth to those capable of reading them correctly. Alchemy continues as well. Newton's alchemical manuscripts eventually total over 1 million words, dwarfing his published scientific output. He conducts experiments in a laboratory adjacent to his Trinity College rooms, then later in London. He is searching for the philosopher's stone, the substance that transmutes base metals into gold and perhaps grants immortality. Modern historians debate what Newton really believed about alchemy. Was he a true believer seeking literal transmutation? Or did he understand alchemy metaphorically as a philosophical system encoding deeper truths? The manuscripts suggest genuine belief. Newton takes alchemical claims seriously. He experiments systematically. He seeks patterns and principles. The alchemical laboratory is Newton's other secret world. Where his optical and mathematical experiments can be discussed publicly, his alchemical work must remain hidden. The Royal Society would tolerate discussions of transmutation as abstract philosophy, but active experimental alchemy is suspect, associated with fraud and delusion. Newton does not care about societal opinion, but he values his privacy. The laboratory is locked, only he has the key. Inside, the space resembles an ancient apothecary. Furnaces for heating substances stand against walls stained black with smoke. Glassware of various shapes, alembics, retorts, cucurbits, line shelves. Jars contain substances with evocative names: antimony, vitriol, aqua fortis. Manuscripts in Newton's hand document experimental procedures in meticulous detail. Take 2 parts, mercury philosophical. Heat gently until vapors rise. Collect the vapors in a sealed vessel. Cool slowly, observing color changes. The language mixes precise measurement with mystical terminology. Newton spends hundreds of hours heating metals and minerals, observing their transformations, recording colors and textures and behaviors. He breathes fumes that modern chemists know are toxic: mercury vapor, lead compounds, sulfur dioxide. The cumulative exposure damages him slowly, contributing to the tremors and irritability of his later years. But at the time, he does not recognize the danger. The work feels important, even sacred. What is he actually doing? Partly, he is conducting genuine chemical investigations. Many of Newton's observations about how substances combine and transform are accurate by modern standards. He is discovering real chemistry, even if he interprets it through alchemical frameworks. The behavior of acids and bases, the properties of metals, the processes of crystallization, Newton documents all of this carefully. But there is also genuine mysticism. Newton believes that metals have gender, that substances have philosophical essences distinct from their material forms, that ancient adepts discovered secrets now lost to common knowledge. He reads Hermes Trismegistus and Nicholas Flamel with the same seriousness he reads Descartes and Galileo. For Newton, these are all approaches to truth, different languages describing the same underlying reality. The alchemical work connects to his theology in ways that seem bizarre to modern minds but were logical for Newton. God created the universe with hidden patterns and purposes. Nature contains secrets accessible only to those pure and diligent enough to discover them. The Bible encodes knowledge through symbolism and allegory. Alchemical texts encode knowledge similarly. Both require interpretation, both reveal truth to the prepared mind. Newton sees himself as an initiate, someone capable of reading the encrypted messages God has left in Scripture and nature. Does he ever achieve transmutation? The manuscripts are ambiguous. Newton describes experiments where substances change color and properties, which he interprets as progress toward the great work. But modern analysis suggests he was observing ordinary chemical reactions: oxidation, crystallization, alloy formation. Whether Newton recognized this or genuinely believed he was approaching mystical transformation remains unclear. What is clear is that he never stopped trying. Even in his 70s, serving as Master of the Mint and Royal Society President, Newton continues alchemical experiments
still seeking the stone, still believing the secret can be found. The contradiction is stark. The man who established mathematical physics as the foundation of understanding nature devotes more effort to alchemy and theology than to science. The founder of the mechanical worldview believes the universe contains hidden spiritual forces that can be manipulated through ritual knowledge. This does not fit the standard narrative of Newton as pure rationalist. It reveals instead a mind-seeking unity beneath surface diversity, convinced that natural and supernatural knowledge can be integrated into a single coherent system. In 1705, Queen Anne knights Isaac Newton. He is 62 years old, the first scientist knighted for scientific achievement rather than administrative service. It is recognition of his eminence. He is Sir Isaac now, a public figure, elderly but still sharp. He continues as Royal Society President, as Master of the Mint. He oversees the publication of revised editions of his works. The Principia appears in a second edition in 1713 with revisions and responses to critics. The later years are marked by declining health but continued mental acuity. Newton suffers from kidney stones, a painful condition he bears stoically. He maintains his household, his administrative duties, his scholarly correspondence. Catherine Barton remains with him, managing domestic affairs. She marries John Conduit in 1717, and both Catherine and Conduit continue living with Newton. They will become his heirs and early biographers, preserving anecdotes and papers. Newton's religious heterodoxy remains secret until after his death. He confides in a few trusted friends like John Locke, but never makes his Arianism public. When he dies in 1727, the Church of England buries him with full honours, unaware that the man in the coffin denied the Trinity. The irony would have pleased Newton, who spent a lifetime hiding in plain sight, concealing truths that would destroy his position while publicly revealing truths about the universe. The funeral is elaborate. The body lies in state. The coffin is carried by 2 dukes, 3 earls, and the Lord Chancellor. It is buried in Westminster Abbey, the first scientist accorded such honour. Voltaire, visiting England, attends and later writes admiringly of a nation that honours philosophers like princes. The burial site becomes a pilgrimage destination. Newton's tomb, designed by William Kent, features a sarcophagus topped with a reclining figure and a globe showing constellations and the path of the 1680 comet, whose orbit Halley calculated using Newtonian mechanics. The funeral procession through London streets draws enormous crowds. People line the route, silent and respectful, understanding that they are witnessing history. Many do not fully comprehend Newton's achievements. The mathematics of the Principia remains inaccessible to all but a few dozen people in England, but they understand greatness when they see it honoured. Here is a man born in an obscure village, rising through intellect alone to become a knight and national treasure. The story resonates with British pride in merit over inherited privilege. Westminster Abbey has hosted monarchs and nobles for centuries, but never before a scientist. Newton's burial here represents a seismic shift in what society values. Knowledge, not just power or blood, merits the highest honours. The Royal Society members who attend feel this acutely. Their work, often dismissed as eccentric hobby or irrelevant abstraction, has been validated. If Newton can be buried among kings, then natural philosophy matters, then understanding nature matters, then their own work matters. The tomb itself becomes a shrine. Visitors in subsequent decades come to pay respects, to leave flowers, to contemplate mortality and immortality. Newton's physical body decays beneath the stone, but his ideas grow stronger with time. Each generation finds new applications for his laws. Engineers use them to build machines. Astronomers use them to predict celestial events with uncanny accuracy. The Principia's authority becomes almost scriptural. If Newton said it, it must be true. But there is also critique.
Continental philosophers, particularly in France and Germany, resist the Newtonian worldview. They find action at a distance too mysterious, too much like medieval occultism. They prefer Descartes' mechanical philosophy, where everything is explained by direct contact between particles. The debate between Newtonian and Cartesian physics occupies European intellectuals for decades. Gradually, Newton's superior predictive accuracy wins, converts. By the mid-18th century, Newtonianism has triumphed. The tomb's symbolism is rich. The reclining figure represents Newton at rest after a life of labor. The globe shows the heavens he explained, the cosmos he made comprehensible. Latin inscriptions praise his penetration into nature's secrets, his illumination of dark mysteries. Absent from the tomb, tellingly, is any religious symbolism beyond generic piety. No crosses, no saints, no biblical scenes. The tomb honors human reason, human achievement. It is almost secular, which would have irked Newton given his profound, if heretical, religiosity. He saw his science as revelation of God's design. Later ages remember the science and forget the theology, but who was actually buried that day? The question is not flippant. Newton was so many things so contradictory that reducing him to a single identity falsifies him. He was the mathematical physicist who established laws governing motion and gravitation. He was the alchemist, searching for transmutation and spiritual enlightenment. He was the theologian, convinced he had decoded biblical chronology and exposed Trinitarian heresy. He was the bureaucrat who reorganized the mint and pursued counterfeiters. He was the vindictive academic who destroyed rivals and nursed grudges for decades. He was the abandoned child who never formed intimate relationships and died without heirs. He was the genius who saw further than anyone before him and the damaged person who could not tolerate being questioned. The scientific revolution narrative positions Newton as the culmination, the figure who completed the transformation from medieval to modern thinking. Copernicus displaced Earth from the center of the cosmos. Galileo established mathematical description of motion. Kepler found the laws of planetary orbits. Newton unified it all, showed that the same mathematics governing falling bodies also governs orbiting planets, proved that the universe operates by comprehensible laws. This narrative is true but incomplete. It makes Newton the hero of rationality, the man who banished mystery and superstition. But Newton did not banish mystery. He relocated it. The universe operates by mathematical laws, yes, but where do those laws come from? Newton's answer is God. Gravity is the mechanism by which God maintains cosmic order. The laws of motion reflect divine design. The universe is a clockwork, but a clockwork that requires a clockmaker. Newton's natural philosophy is inseparable from his theology. He studies nature to understand God's creation. The division between science and religion that later centuries impose would have been incomprehensible to him, and the alchemy reveals something deeper. Newton was searching for hidden knowledge, for secrets concealed in ancient texts and natural processes. He believed such knowledge existed, that past ages possessed wisdom subsequent generations lost. The philosopher's stone was not metaphor but real object, and Newton intended to discover it. This is not rational in the modern sense. This is a different epistemology, one where empirical investigation and spiritual insight are two paths toward the same truth. Modern physics exists because Newton established mathematical laws and experimental verification as the path to understanding nature. But Newton himself believed he was rediscovering ancient wisdom, decoding secrets that biblical prophets and pre-Socratic philosophers had known. He saw himself not as an innovator, but as a restorer, bringing back knowledge that had been corrupted or hidden. The famous line about standing on the shoulders of giants, "If I have seen further, it is by standing on the shoulders of giants." This appears in a 1675 letter to Robert Hooke. Later scholars suggest it may be an insult. Hooke was short and hunchbacked. The image of Newton standing on Hooke's shoulders to see further is perhaps mockery disguised as modesty. This is the Newton problem. Every attempt to simplify him falsifies him. The rational scientist was also the mystical alchemist. The mathematical genius was also the biblical chronologist who dated creation to 4000 BC. The man who revealed universal laws also believed in prophecy and hidden codes. The founder of modern physics spent more time on subjects modern science rejects than on subjects it celebrates, and his psychology remains genuinely disturbing. The vindictiveness toward Hooke and Leibniz goes beyond professional rivalry into obsessive persecution. Newton used institutional power to destroy people who questioned him or claimed their own achievements. He held grudges until enemies died, then celebrated their deaths by publishing work he had suppressed while they lived. When he became Royal Society president, he allegedly destroyed the only portrait of Hooke. The story is disputed, but it fits the pattern. Newton erased people who challenged him. Where does this come from? The obvious answer is childhood abandonment. The 3-year-old left by his mother develops into an adult who cannot tolerate the possibility of being supplanted or overlooked. Priority disputes are not about credit. They are about existence. To be second is to be worthless. To share credit is to be abandoned again. Newton must be first, must be irreplaceable, or he is nothing. But this does not diminish the achievement. If anything, understanding Newton's psychology makes the achievement more remarkable. A deeply damaged person, emotionally stunted, incapable of normal relationships, spent solitary decades conducting investigations no one asked for, solving problems no one else could solve, revealing patterns no one else saw. The wound that made him incapable of human intimacy also drove him toward nature with an intensity that produced unprecedented insight. He could not connect with people, so he connected with the universe, and the universe yielded its secrets. The Principia remains one of the most important books ever written. For 2 centuries, until Einstein's relativity, Newtonian mechanics defined physics. Engineers still use Newton's laws to build bridges and launch satellites. The conceptual framework, force, mass, acceleration, action, and reaction, this structures how we think about physical reality. The mathematical methods Newton developed, even though he kept calculus unpublished for years, established the template for applying mathematics to nature. Before Newton, mathematics described nature. After Newton, mathematics explained nature. The book's influence extends into unexpected domains. Political philosophers like John Locke apply Newtonian reasoning to society, seeking laws of human behavior as universal as laws of motion. Economists attempt to find mathematical principles governing markets and trade. Even theology absorbs Newtonian concepts, with deists pointing to the clockwork universe as evidence of an orderly creator. The Enlightenment's faith in reason, its belief that all problems yield to rational analysis, owes enormous debt to Newton's demonstration that even the heavens obey comprehensible laws. But this influence brings responsibility. The mechanistic worldview Newton established makes the universe seem deterministic. If everything follows laws, where is free will? If humans are just arrangements of matter obeying physical principles, where is moral responsibility? Philosophers grapple with these questions for centuries. Newton himself did not worry about them. He believed God granted human souls exempt from mechanical determination, but his successors, lacking his religious conviction, confront a world that seems to leave no room for meaning or purpose. The Principia also changes how knowledge is pursued. Before Newton, natural philosophy mixed observation, speculation, and ancient authority. After Newton, the standard is mathematical proof. You must show your work. You must derive conclusions from first principles. You must predict observations that can be tested. This methodology, born from Newton's rigor, becomes the defining characteristic of modern science. It is not enough to have intuitions or insights. You must demonstrate them with the same certainty Newton demonstrated universal gravitation. The book's difficulty is notorious. Even brilliant contemporaries struggle with it. The geometric proofs require sustained concentration and mathematical sophistication. Many readers give up after the first few propositions. This inaccessibility actually enhances the Principia's authority. It is difficult, therefore it must be profound. It is incomprehensible to common people, therefore it must contain uncommon truth. The mystique surrounding the Principia makes Newton seem not just smart but superhuman, a being who operates on a plane above normal intellect. But Einstein did supersede Newton. In 1915, general relativity showed that gravity is not a force, but the curvature of space-time by mass. Newton's inverse square law is an approximation, accurate for weak gravitational fields and low velocities, but breaking down near black holes or at speeds approaching light. The Newtonian universe of absolute space and time dissolves into the relativistic universe of space-time intervals and frame-dependent measurements. Does this invalidate Newton? No, it contextualizes him. Newton discovered the physics of the observable universe at human scales and velocities. His laws work for everything from baseballs to planets. They fail only in extreme conditions Newton could never observe. He was brilliantly correct within a domain he had no way to exceed. The fact that his physics is incomplete does not diminish its achievement. It places Newton in the tradition of all scientific theories, powerful within their domain, superseded when that domain expands. And Newton understood limits. The Principia explains how gravity operates but not why. Newton famously refuses to feign hypotheses about gravity's cause. He can describe its mathematical behavior but not its underlying nature. This frustrates critics who want mechanical explanations, but Newton holds firm. The mathematics works, the predictions match observations. That is sufficient. The deeper cause, if knowable at all, remains hidden. This methodological restraint is crucial. Newton establishes that natural philosophy can progress without complete understanding. You do not need to know why gravity exists to use its laws. You do not need ultimate causes to make accurate predictions. This pragmatism becomes central to scientific method. Later, physics will uncover electromagnetic force, strong and weak nuclear forces, quantum mechanics. But the Newtonian template remains. Find mathematical laws that predict observations, test them rigorously, accept that deeper questions may remain unanswered. The legacy extends beyond physics. Newton's success convinced Enlightenment thinkers that reason could unlock all mysteries. If the universe obeys mathematical laws, perhaps society does too. Perhaps politics, economics, ethics can be systematized like mechanics. This is naive. Human behavior is not governed by inverse square laws, but it shows Newton's cultural impact. He made the universe comprehensible, and that comprehensibility suggested all problems might yield to rational analysis. But the shadow legacy is also real. The view of nature as machine, operating by blind laws without purpose or meaning, this creates the disenchantment Max Weber will later describe. If the universe is clockwork, where is wonder? If everything reduces to particles and forces, where is significance? Newton himself did not feel this disenchantment. He saw divine design in natural law, but later generations, stripping away the theology, confront a cosmos indifferent to human concerns. We are accidents in a mechanical universe, our lives brief and meaningless unless we create meaning ourselves. This is unfair to Newton. He did not intend to create existential despair. He intended to reveal God's glory through understanding God's creation. But intentions and consequences diverge. The mechanistic worldview Newton established becomes, in secularized form, the foundation for a universe without transcendence. We live in a world Newton made possible, and we cannot entirely decide whether to thank him or curse him for it. Return now to Kensington, March 1727. The old man dying in his bed has lived 84 years, longer than most of his contemporaries. He has been Master of the Mint for nearly 3 decades. He has been Royal Society President for 24 years. He has been knighted, celebrated, memorialized in poems and portraits. His Principia stands as one of civilization's supreme achievements. He has no wife, no children, no intimate relationships to speak of. Catherine Barton and John Conduit are present, but Newton has lived fundamentally alone. The room where Newton dies is filled with evidence of his obsessions. Manuscripts pile on tables and shelves, not just scientific works, but theological treatises, chronological studies, alchemical experiments. Books line the walls, many bearing Newton's marginal annotations, his agreements and disagreements with authors long dead. The window looks out on London, the city that has been his home for 3 decades. But Newton has never truly belonged to London or to any place. He has lived in his mind in the abstract realm of mathematics and natural law. Catherine Barton sits nearby, worried but not surprised. Newton has been declining for months. The kidney stones have grown worse, the pain more constant. He has refused most treatment, accepting only basic palliatives. At 84, having lived longer than anyone in his family, he seems ready to accept mortality. Or perhaps accept is wrong. Newton does not accept in the sense of submitting. He observes his own decline with the same detached curiosity he once applied to falling apples and refracting light. Death is one more phenomenon to experience, one more transition to witness. John Conduit, Catherine's husband, has been keeping notes for a biography. He has asked Newton questions about his early life, about the discoveries at Woolsthorpe, about the composition of the Principia. Newton has answered some questions clearly, others evasively. Certain topics he will not discuss: his mother's abandonment, his feuds with rivals, his theological heterodoxy. Conduit suspects there are depths he will never access, secrets that will die with Newton. What does he think about in these final hours? Does he review his life with satisfaction or regret? Does he contemplate the natural philosophy he revolutionized, or the alchemy that consumed so much time without yielding transmutation? Does he think about the mother who left him, the rivals he destroyed, the discoveries he withheld from the world for decades? We do not know. He leaves no record of final thoughts. The last words, if there were any, are not preserved. There are moments when Newton seems to drift, consciousness dimming, then returning. During these twilight states, does he see visions? Does he review memories? Biographers later speculate, but cannot know. The interior life of the greatest scientific mind in history remains, at the end, utterly private. He arrived in the world alone, premature and fragile, and he leaves it alone, elderly and accomplished, but the fundamental solitude has never changed. Catherine holds his hand at one point, offering human warmth in the final hours. Newton does not pull away, but neither does he seem particularly aware of the gesture. His attention is elsewhere, turned inward, or perhaps beyond. The man who decoded the universe's mechanical laws confronts now the ultimate mystery, the one question his mathematics cannot answer. What happens when consciousness ceases? Where does the mind go when the brain stops? Newton, who demanded rigorous proof for every proposition, must now proceed on faith or face annihilation without understanding. He dies in his sleep. The body is examined. The cause appears to be complications from kidney stones, a painful condition he has endured for years. The physical suffering is over. Whatever psychological suffering he endured, and the evidence suggests it was profound, that is over too. In the immediate aftermath, Catherine and Conduit begin the difficult task of sorting through Newton's papers. They find the expected scientific manuscripts,
letters from correspondents across Europe, calculations and diagrams. But they also find the unexpected, the massive theological writings denying the Trinity, the alchemical experiments documented in exhaustive detail, the chronological studies claiming to date creation and biblical events with precision. These raise difficult questions. Should they be published? Should they be preserved but hidden? Should they be destroyed to protect Newton's reputation? They choose a middle path. The safe scientific works are preserved for publication. The theological heterodoxy is hidden, shown only to trusted confidants. The alchemical manuscripts are quietly stored away, too voluminous to destroy but too embarrassing to reveal. This editorial decision shapes Newton's legacy for centuries. The public Newton becomes the rational scientist, founder of modern physics. The private Newton, mystic, heretic, alchemist, remains largely unknown until 20th century scholars begin examining the full archives. England mourns. The state funeral is elaborate, the burial prestigious, but the real mourning is intellectual. Natural philosophy has lost its greatest mind. There is no one to replace him. There will not be anyone comparable for generations. Einstein is 2 centuries away. In the meantime, Newton's physics will reign unchallenged, and his methods will define how science is conducted. The manuscripts left behind reveal the complexity. The published works on mechanics and optics are joined by hundreds of thousands of words on alchemy, theology, chronology. Executors sift through papers, deciding what to preserve and what to hide. The anti-Trinitarian theology is too dangerous to publish. The alchemical manuscripts are embarrassing to Newton's reputation as rational scientist. Much is suppressed for centuries. Only in the 20th century do scholars begin examining the full corpus, discovering the strange, contradictory genius who combined mathematical precision with mystical speculation. What are we to make of this life? What does it teach about genius, about science, about human possibility and limitation? First, that genius does not emerge from ideal conditions. Newton was not nurtured and encouraged. He was abandoned, neglected, expected to become a farmer. The trauma that should have destroyed him instead drove him. The wound became engine. He needed to be irreplaceable because he had been replaced. He needed to decode the universe because nothing else could fill the void where human connection should be. This does not romanticize trauma. Trauma destroys more people than it creates, but it reveals that extraordinary achievement can emerge from damage. Second, that rationality and mysticism are not opposed but intertwined. Newton the mathematician and Newton the alchemist are the same person pursuing the same goal: hidden knowledge. The methods differ, but the impulse is identical. He believes the universe contains secrets, and he intends to discover them. Sometimes this means calculus and experiments. Sometimes this means reading hermetic texts and heating mercury in sealed vessels. Modern science excludes the latter, but Newton did not. His unified vision, however strange to us, was psychologically coherent for him. Third, that great achievement coexists with moral failure. Newton's treatment of rivals was cruel. His vindictiveness toward Hooke and Leibniz exceeded professional disagreement and became personal destruction. He used power ruthlessly. He held grudges to the grave. We cannot excuse this by pointing to his discoveries. The physics does not justify the behavior. Newton was simultaneously magnificent and monstrous, and we must hold both in view. Fourth, that knowledge advances through flawed humans, not perfect sages. The scientific revolution was not conducted by serene philosophers dispassionately seeking truth. It was conducted by ambitious, competitive, sometimes petty individuals driven by ego and need. Newton's psychology made him unbearable as a person but relentless as a researcher. The same traits that destroyed his relationships enabled his discoveries. This is uncomfortable but true. Fifth, that what we celebrate is not always what mattered most to the person celebrated. We honor Newton for the Principia. He spent more time on alchemy. We admire his mathematical physics. He considered his theological writings equally important. We have canonized one version of Newton while ignoring aspects he valued. This distorts understanding, but perhaps reflects what endures. His physics remains useful. His theology is historical curiosity. His alchemy is rejected science. We remember what works, not what he thought most important. And finally, that seeing the universe clearly does not mean understanding oneself. Newton decoded celestial mechanics but could not decode his own psychology. He explained why planets orbit, but not why he could not love or be loved. The man who revealed universal laws remained mysterious to himself. This is perhaps the ultimate limitation. We can comprehend the cosmos but not our own hearts. We can predict eclipses centuries in advance but not know why we hate those who question us. The Dying Man in Kensington contained all these contradictions: genius and damage, rationality and mysticism, achievement and failure, pride and insecurity. He changed how humans understand nature, and he remained fundamentally alone. The force that holds moons in orbit, that pulls apples downward and planets around stars, this force he named and quantified. But the forces that should have held him to other humans, that should have given him family and friendship and love, these forces he could never master. In the end, what remains is the work. The Principia endures, the laws of motion endure. The mathematical framework endures. Newton's psychology, his feuds, his alchemy, these are biographical details that contextualize but do not define his legacy. 200 million years from now, if humans still exist and remember anything of this era, they will remember that someone named Newton explained how objects move and why planets orbit. They will not remember that he hated Robert Hooke or believed in transmuting lead to gold or denied the Trinity. But we, closer to his time, inhabit the complexity. We know the wounded child and the vindictive adult and the solitary genius. We know the man who would not publish calculus for decades and the man who orchestrated campaigns to destroy rivals. We know the natural philosopher and the alchemist and the heretic. We know, in short, the human being, not the icon. And knowing this, what do we learn? That greatness is not purity. That revolutionary insight emerges from damaged people. That the mind capable of seeing furthest into nature's laws may be least capable of navigating human relationships. That genius is not virtue. That the person who changes the world may be the person least suited to live peacefully in it. Isaac Newton died 84 years after being born too small to survive. He outlived everyone who abandoned him, everyone who questioned him, everyone who rivaled him. He died famous and wealthy and utterly alone, having revealed laws that will govern physics for centuries, having spent his private hours on pursuits history would consider madness. He unified heaven and earth with equations and could not unify the warring parts of himself. The irony is profound and inescapable. The man who explained why the universe holds together could not explain why he could not form lasting human bonds. The thinker who demonstrated that all matter attracts all other matter through gravitation remained repelled by emotional intimacy. The genius who proved that action and reaction are equal and opposite could never balance the equation of his own damaged psyche. He decoded the cosmos but not himself, revealed universal laws but not the laws of his own heart. The apple falls, the moon orbits. The mathematics explains both, and the man who discovered this dies in a room in Kensington, surrounded by papers containing both the supreme achievements of human reason and the strange obsessions of a mind that could never rest, that could never stop searching for the hidden pattern that would finally make everything make sense, that would finally fill the void left by a mother who walked away when he was 3 years old. History will remember the equations. It will remember the laws. It will remember the man who made the universe comprehensible, but perhaps we should also remember the wound. Perhaps we should acknowledge that genius emerges not from perfection, but from damage, that extraordinary insight can be the compensation for extraordinary pain. Newton's gifts and his wounds were inseparable. The abandonment that should have destroyed him instead forged him into something unprecedented and unrepeatable. This is what remains, the laws that work and the life that didn't, and the question of whether one was worth the other, and the certainty that we will never answer it definitively because the universe Newton revealed is comprehensible, but the universe inside Newton is not, and both are true, and both are real, and both demand our attention if we want to understand what it means when we say, "Someone changed the world."